Hello everyone, this is Math.io today with you, and I hope you had a great day so far. Today we are going to be solving this monster of a calculus problem, including sums, differentiation, limits, and integrals. So let's begin solving this by solving this part right here, the lower bound of the integral. So, natural log of the natural log of b, its degree, the root of 1 over b squared. So first, let us rearrange this by rewriting the square roots as a power, not the square root, the natural log of b degree roots as a power, and this we are going to rewrite it as a negative power, which will give us natural log of b to the negative 2 all to the power of 1 over ln of b. Now, by power rules, we can multiply these two powers together, giving us the natural log of b to the negative 2 times 1 over ln b. Now, by natural log properties, or by all logarithm properties, we can just take this down here, which will give us that this is equal to negative 2 times 1 over ln b times ln b equals. Here we can see that we have ln b on both the numerator and the denominator. You can just cancel them out, which will leave us with negative 2. So we can go right up here in the lower bound of the integral and replace it with negative 2. Okay, now we are going to go for the upper bound of the integral, which is the sum from n equal to 0 to positive infinity of 1 over 2 to the nth power. We have a rule to solve some series like this, which is the first term, which is 1 over 2 to the 0 power, which is 1, times 1 minus the base, which is 1 over 2 to the power of n, the upper bound of n, which is infinity here, minus the first value of n, which is 0, plus 1, all over 1 minus the base. There we go. Here we are multiplying by 1, meaning that it won't change anything to this. You can just get rid of it. And here we have 1 minus 1 over 2 to the infinity, to the positive infinity plus 1. We have 1 over 2 to the positive infinity plus 1, which is positive infinity. The base, the absolute value of 1 over 2 is 1 over 2, which is less than 1, making the limits as the power approaches infinity of this term 0. So we have 1 minus 0 over 1 minus a half. So we have 1 all over 2 minus 1 over 2. 2 minus 1 is 1. So here we have 1 over 1 over 2. You can rewrite this as 1 divided by 1 over 2 making this, we know that when we divide by a fraction, we can multiply by its reverse. So it's 1 times 2, making this equal to 2. This is the upper bound of our integral, which we can just replace here. So we know that the integral, we now know that the integral goes from -2 to 2. Now we are going to go for this limit right here, and by limit rules we can just take this 2 out here. So we can rewrite it in the front, giving us this term right here. So now we are going to calculate only this integral right here, this limit right here. Limit as x goes to positive infinity of x minus the square roots of x squared minus x. In order to, we need to rewrite this in a better way so that we can cancel terms out. Here we can't really do anything with this. So we are going to rewrite this as, we are going to multiply the top and the bottom by the conjugate value of this term right here, which is going to give us the limit of x, the limit as x approaches positive infinity of x minus the square root of x squared minus x. We are going to multiply the top and bottom by the conjugate value, which is x plus the square root of x squared minus x, all over x plus the square root of x squared minus x. Right here. Now here we have a minus b times a plus b. The difference of two numbers times the sum of two numbers, which we can write as, first let us write the limit sign here. This gives us the first term squared minus the second term squared, all over this term right here. Okay. So this gives us the limits as x approaches positive infinity. So now we can just cancel the square roots in the square, giving us the limits as x approaches positive infinity of x squared minus x squared. Minus with minus gives us plus x, all over this, which is x plus square root of x squared minus x. Now what we can do here, we can cancel out these two here, because a number minus itself is 0. And now we have x on top. Okay. The limit as x approaches positive infinity. X approaches positive infinity, meaning that x is positive. It's a positive number, so meaning that x is equal to its absolute value. So what we can do here, we have x over x plus the square root of x squared minus x. Okay. What we can do is factor out everything by the absolute value of x or x. It's the same thing. Here we have x and x. We can just rewrite them as the absolute value of x. No issues because x is positive anyways. This is equal to the limit as x approaches positive infinity of the absolute value of x over the absolute value of x. Here we are going to factor this out, to factor the square root of x squared, which is the absolute value of x. Okay, so you are going to factor out with the absolute value of x. X squared, the square root of x squared over x, the square root of x squared is basically 1. No, x squared divided by x squared is 1. X divided by x squared is 1 over x. So we have minus 1 over x. Okay. So here we have the limits of x approaching positive infinity of 1 over x. This is basically 0. This approaches 0 right here, this number here. It approaches 0. We can, in the next step, just replace it by 0. We aren't breaking any limit rules here. So we have the limits as x approaches positive infinity of the absolute value of x over the absolute value of x factor 1 plus this. This is 1 minus 0. We can just rewrite the square root of 1 minus 0, which is the square root of 1, which is 1. So yeah, this is what we have here. We can just cancel out these terms. And we are left with 1 over 1 plus 1, giving us 1 over 2. We can go right to the top and replace the limits with its newfound value, which is 1 over 2. So we are going to replace this with 1 over 2. Here we have 2 multiplying 1 over 2. We can just cancel them out, leaving us with the final value, which is 1. Yep, we can just write it right here. Okay, now to finish, we are going to evaluate this part right here, the numerator of the fraction of the integral. Okay, so now we are going to compute this part right here. First, let's rewrite it. It's 1 over 2 t to the 4th power times the derivative of natural log of t to the negative 1 over t to the negative 3. Right here. So, what we are going to do first is deal with these powers right here. If we have the same base and a to the power of a number over a to the power of another number, we can just factor it out by writing it as a to the power of the first number minus the second number, which is going to look like this. So we have first, let's copy the rest, 1 over 2 t to the 4th power times the derivative of the natural log of t to the power of negative 1 minus negative 3, like this. So, negative minus a negative number. It's like multiplying by negative 1 times negative 1, which is 1, meaning that this becomes 3. It becomes 3. So, we are going to rewrite this as 1 over 2 t to the 4th power times the derivative of the natural log of t to the negative 1 plus 3. Negative 1 plus 3, it's 3 minus 1, it's 2. You can just rewrite it as 2. So now, we are going to deal with this. So first, let's 1 over 2 times t to the 4th power times the derivative of, first, by log properties, we can just get this square out here. We can just put the power down, giving us 2 natural log of t. Here, what's the derivative of the natural log of t? It's 1 over t. So the derivative of 2 natural log of t is 2 over t, or 2 times 1 over t. So let's rewrite it as 1 over 2 times t to the 4th power times 2 times the derivative of the natural log of t, which is 1 over t. Okay, now we are left with this. We can cancel out this and this, leaving us with t to the 4th power over t. T to the 4th power is t to the 3rd power times t over t. Cancel these out. We are left with t to the 3rd power, which we can rewrite here. Okay, we are going to erase this part right here and replace it with its new value, which is t to the 3rd power. Okay, so now we are left with this integral, the definite integral from negative 2 to 2 of 1 over t to the 3rd power with respect to t. So let's rewrite it, and we are going to be left with negative 2 to 2, the integral from negative 2 to 2 of 1 over t to the 3rd power dt. First, we are going to be tempted to apply the rules, integration rules, to get a simple value for this. Normally, the undefinite integral of this is 1 over t of this function right here is the indefinite integral of t to negative 3 dt. We are tempted to just divide by this and raise the power, making this 1 over negative 3 plus 1 t to negative 3 plus 1. We are tempted to do this and then get 1 over negative 2, which is like this, and then we get t to the negative 2. We are going to get negative 1 over 2 t squared, and then we are going to replace it with the upper bound minus the lower bound. We are going to get a certain number, and that would be completely wrong. And the reason for that is, if we look at this function, it's going to be a hyperbolic function that looks something like, first let's draw a graph like this. This function right here is going to look something like this. If we just take the indefinite integral at 2 and we subtract it with the indefinite integral at negative 2, we would be forgetting the fact that the function isn't continuous right here. There is a discontinuity at 0. It's meaning that the function isn't continuous, so we need to break this into 2 integrals. So we can go for the integral from negative 2 to 0 of 1 over t to the 3rd dt, plus the integral from 0 to 2 of 1 over t to the 3rd dt. This would be the correct procedure. But if we try to compute this diverges and this diverges. Both are equal to positive infinity. So we can't go that way. Here we need to make some observations. First, let's erase this. So we are going to take the values of 2 and negative 2, which are, let's say, they are like somewhere like this, somewhere like here. Okay, let's say that this is 2 and that this is negative 2. Yeah, that looks about right. So this function has an odd power, making the function odd. meaning that the function is symmetrical around the origin, meaning that this part over here is equal to this part over here as long as this value and this value are equal. This only works if the function is even around the origin, which is the case for this one. Meaning that this area and this area are equal, but this part is over the x-axis, but this part is below the x-axis. So this and this are equal in area, but are completely opposites. Meaning that this plus this is like saying this area minus this area, which gives us 0. Meaning that this integral right here is equal to 0, or at least the surface under the curve between these values. So we can go and work this out inside our final answer. So our final answer is going to be the arctan of 0. The arctan of 0. First, to solve this, let's go to the unit circle. How do we know the tan of a certain angle? Knowing that this is the unit circle, meaning that this distance is equal to 1, same for this one. First, let's draw the tangent to the circle at the points x is equal to 1 and y equal to 0. Meaning right here. Or here we are working with the radius and angle. So yeah, the tangent to the circle at this point right here. Okay, if we want our tangent to be equal to a certain value, it means that the distance between, if we go for the angle and we project it on this line, the height here is the tangent of that angle. Right, so if we want the tangent of our angle to be equal to 0, we need our angle to meet certain values. These values are, first, if we want our line to cut this, we need it either to be 0, so that it cuts it right here, or it could be half a rotation here, so it's pi, so it cuts it as well. But we can continue rotating till we reach 2 pi. Same thing. 3 pi, same thing. 4 pi, same thing. So, and same thing for negative values if we rotate the other way around. So, in order to get a tangent that's equal to 0, we need an angle that's equal that's equal to a multiple of pi. So we are going to rewrite this as tan of k pi is equal to 0. K being a positive or negative integer. Right. So, we know that 0 is tan of k pi. We can go right here and replace 0 by tan of k pi. There we go. Let's rewrite this k a bit better. Okay. Tan and arctan are reciprocal functions, so we can basically cancel them out, leaving us with the answer that's beasts of a problem, the answer to it is k pi, such as k is a positive or negative integer. So, there we have it. Thank you for watching, and please consider subscribing. It will really boost me and encourage me to post some more challenging content like this. Thank you for your time, and I hope you learned something new. Goodbye.